Good morning. Welcome to the lecture on numerical integration. The process of finding the approximate values of definite integral I is integral from a to b y dx is called numerical integral. The interval a b is divided into n equal parts of the width h p minus k by n. Let a equals to x naught less than x naught plus h less than x naught plus 2h less than etc. is less than x naught plus nh equals to b be the points of division. Note that when we divided the interval AB into n equal parts, there will be n plus 1 values of x. That is, x is a equal to x naught, x1, x2, etc. xn is equal to b. Second point we need to note down here is if y is in n plus 1, the number is referred as n plus 1 ordinates. So, we can conclude that if there are n plus 1 ordinates, there must be n equal divisions. We come across with 3 rules depending on the number of divisions we make in interval. First one is Simpsons one-third rule. This Simpsons one-third rule I is integral from a to b y dx is equal to h by 3 of y naught plus yn plus 4 times of y1 plus y3 plus etc. yn minus 1 plus 2 times of y2 plus y4 plus etc. yn minus 2. It's very easy to remember the formula. That is, since it is one-third rule, we are multiplying with h by 3 and first term and the last term, that is y0 and yn, is added as a first group, and in the second group, that is 4 times of all the odd suffixes will be added, that is y1 y3 etc. And all the even suffixes, that is y2 y4 etc. are added and then multiplied with 2. Coming to the second one, I is integral a to b y dx is 3h by 8. Again, first term and the last term, that is y0 plus yn plus 3 times of y1 plus y2 plus y4 plus y5 etc. yn minus 1 and 2 times of y3 plus y6 plus etc. yn minus 3. How to remember this is first and the last term should be added. 3 times of all the suffixes except the multiples of 3 and 2 times of all the suffixes with 3 multiples of 3. Next comes the Vedas rule. In the Vedas rule, we have 2 cases. The first case is when n is equals to 6. It is given by I equal to integral a to b y dx equal to 3h by 10. Again, y0 plus y6 because n value is 6, that's the end one, plus 5 times of 1 y1 plus y5 plus y2 plus y4 plus 6 times of y3. This is the formula which can be used in order to find integral when n is divided into 6 parts. Second one, when n is 12, that is when the interval is divided into 12 equal parts, we get I as integral a to b y dx equal to 3h by 10 y0 plus y12, that's the last term, plus 5 times of y1 plus y5 plus y7 plus y11 plus y4 plus y2 plus y8 plus y10 plus 2y6 plus 61 y3 plus y9. This is the Vedas formula. We get it for n is equals to 12. Here are some points to remember as a note. When to apply 1/3 rule or 3/8 rule or Vedas rule. When n is multiple of 2, we can apply Simpsons 1/3 rule only. When n is multiple of 3, we can apply Simpsons 3/8 rule. When n is multiple of 6, we can apply Vedas rule, and not only that, we can also apply 1/3 and 3/8 because 6 is multiple of 2 as well, 3. So when we have a problem which has n multiple of 6, we can use all the 3 methods and we can compare the solution. Let's have an illustration. Evaluate integral 0 to 6 of 3x square dx by dividing the interval 0, 6 into 6 equal parts by applying the Simpsons 1/3 rule. Solution. Consider I equal to 0 to 6 3x square dx in the interval 0, 6, where a is 0, b is 6, n is 6. To find the value of h, that is upper limit minus lower limit by n. So we get 6 minus 0 by 6, which implies h is 1. Now x is taken as 0, 1, 2, 3, 4, 5, 6. That is, we will start from 0 to 6 with an increment of 1 so that the interval is equally divided. Now, when x is taken as 0 to 6, we can calculate y by taking the function y as 3x square. When we put the values of x as 0 to 6, we get the corresponding values of y as 0, 3, 12, 27, 48, 75 and 108. Respectively, these can be named as y0, y1, y2, etc., y6. When we name this easily, we can use the formula and obtain the solution. The Simpsons 1/3 rule is As we discussed, I is h by 3 of y0 plus y6 plus 4 times of y1 plus y3 plus y5 and 2 times of y2 plus y4. That gives on substitution I is equal to 216. Thank you.